everyone, my name is Saborna Berries from Berry Science Lab, and welcome back to Electromagnetism. Today, we're finishing off Chapter 2 of Griffith's Electrodynamics with the delta function, divergence, and curl. So, what's the delta function, first of all? Well, the Dirac delta function is actually a really special function. I don't know if you can even really call it a function, because it's not very well defined by itself. It's only well defined when you put it into an integral. So, what is the delta function? Well, imagine this. I'm going to draw a set of piecewise functions. So the first one is going to be from negative 0.5 to 0.5. It's going to take value 1. And then everywhere else, it's going to be 0. So we're going to call this f1. So f1 of x is equal to 1 if the absolute value of x is less than or equal to a half, 0 otherwise. Now I'm going to raise the stakes for f2. What I'm going to do is I'm going to double the height and halve the width. Oh, Jesus. So f2 is going to be 2 if the magnitude is less than or equal to a fourth, and 0 otherwise. And you might notice that its integral from minus infinity to infinity is still equal to 1, which is the same as the integral for f1. Now let's look at f3. We have that f3 of x is going to be 4 if the absolute value of x is less than an eighth, 0 otherwise, and so on and so forth, with fn of x being equal to 2 to the n minus 1 if the absolute value of x is less than or equal to 1 over 2 to the n, and 0 otherwise. So the integral of all fn of x from minus infinity to infinity is still equal to 1. But all of its mass keeps getting centralized around the origin. And eventually, it should, you'll notice that the spike around 0 is eventually going to approach 0 width in infinite height. And it's going to be 0 everywhere outside that specific point. That's what the delta function is. The delta function is that function is the limit as n approaches infinity of fn of x. So, why is this useful? Well, let me introduce you to a quick example. Let's say we take the radial vector divided by the magnitude of the radius, or the radius itself, squared. So, what does this give us? Another way to write this would maybe be, well, this is the radial unit vector, which is just going to be, the actual radial vector over r cubed. So, actually this shows up in Coulomb's law. This is just going to be equal to, for instance, x over the square root of x squared plus y squared cubed, comma y over the square root of x squared plus y squared cubed. But enough about that. But enough about that. So how do we find the divergence of this field? Well, let's draw a quick sketch first. This looks like it should point outward and gradually decrease in strength over time because of the r squared factor. And so, clearly, the divergence of this function should be equal to something very positive, right? Well, let's try taking it. We rewrite this in its original glorious form. X over x squared plus y squared to the 3/2, comma y divided by x squared plus y squared to the 3/2. And now we have to take the divergence. So we write partial x, partial y dot this, and this gives you partial x of this expression plus partial y of this expression. So how do we differentiate this? Well, it looks like it's going to be the product rule. So we write x over x squared plus y squared to the 3/2. By the product rule, the derivative of this is equal to 1 over x squared plus y squared to the 3/2 plus x times, what's the derivative of this? Well, that's x squared plus y squared to the minus 3/2. And so when you take the derivative of that, that's going to be minus 3/2 x squared plus y squared to the minus 5/2. And then by the same rule, you also have to take the derivative of what's inside, which gives you an extra factor of 2x. So you get this. So this is going to be what? Minus 3x squared divided by x squared plus y squared to the minus 5/2. Okay, oh, to the positive 5/2, sorry. So, I mean, things look fine so far. Now, what happens if we try y? Yeah, everything checks out. Now, what happens if we try this with y? Well, logically, everything should just be flipped, right? The variables here should just have switched names. So if we take d dy of this, that should give us 1 over x squared plus y squared to the 3/2 minus 3y squared over x squared plus y squared to the 5/2. Also keep in mind, 3/2 and 5/2 are not 2 apart, they're 1 apart. And so actually, I write x squared plus y squared minus 3x squared divided by x squared plus y squared to the 5/2, which becomes y squared minus 2x squared. And so, similarly, the other end should be 2x squared minus, x squared minus 2y x squared plus y squared to the 5/2 back in, and you get what? Well, this is minus 1 over x squared plus y squared to the 3/2. Okay, so this is a paradox. Not only is this obviously going to be always positive, which means that the whole thing is going to be always negative, but also this is totally undefined at 0, what it very much should be. So, I mean, what's going on here? Well, as it turns out, this function is actually perfectly described. This function's divergence is perfectly described by 4 pi times the delta function. Why is this? Well, when you think about it, what is r over r cubed, or magnitude of r over r squared, actually going to look like as you get closer and closer and closer to the center? What's the magnitude of this? Well, r's magnitude is 1, and so the magnitude of this should be 1 over r squared. So, logically, that means that the magnitude should diverge as you get closer and closer. It's almost like it becomes infinity, it's 0, and then slowly diverges away from that as things spread out. And of course, when it comes to divergence, intuitively, all that spread goes to 0, and the only thing left is the delta function at the origin. So, This is actually one of the biggest use cases of the delta function. The divergence of something this similar to Coulomb, this similar to the electric force generated by Coulomb's law, can be perfectly described by a delta function. And now you might also realize that a delta function is not well defined. I mean, delta of 0 is what? Infinity? It doesn't make that much sense, actually, to talk about the delta function unless we're talking about it in terms of an integral. So the only time this is understandable or intelligible is when you're taking the integral of the divergence. And of course, that only takes place when we're using the divergence theorem. So the delta function intricately connects to the heart of one of the most common vector fields that you're going to see in all of electrodynamics, which is why you're going to keep seeing it. Thank you everyone for watching, and